So this is an exciting lecture because here we lift some of the magic of how the execution of a program happens in a processor. We look at the binary representation of instructions and how we can translate the binary encoding instruction in what the instruction actually has to do. So when we represent instructions, they are the code for the machine and they are encoded in binary representation. That binary representation of the instruction is called machine code. This is in contrast with assembly code. That's something that is usually manipulated by humans. In RISC-V, the instructions are encoded in 32-bit instruction words. There is a small number of formats for encoding the operations. And the register number, etc., are very regular. So there is lots of regularity in the instruction set architecture of RISC-V. And that's a good thing because it allows for lots of simplification in the hardware implementation of the architecture. The register names in RISC-V, we name them from T0 to T6, but note that T0 to T2 are in X5 and X7, T3 to T6 are in X28 to X31, S0 to S1 are in X8 to X9, and S2 to S11 are in X18, X27. The choice of mapping these registers to this specific register number was made by the hardware designers, and it's just something that was done, and we need to work with what we have. What we're going to see in the encoding instruction is that we need to know the number of each register in order to decode an instruction. So let's start with a type of instruction that's fairly common that's called the R type instruction. R stands for registers. So this instruction that we'll look first is the add. We are adding S7 and S5, and the result is going to T0. So because we're going to be encoding this instruction binary, we need to know the number of each one of those registers. T0 is the register 5, S7 is the register 23, and S5 is the register 21. So the binary representation for this instruction will have this format, where we have several different elements that we're going to be examining. Each one of those rectangles with a number inside, we call this a bit field, because there is a sequential bits that are used to represent that information. So S5 is encoded as the register source 2, and because this is the register 21, the number 21 will going to appear in that bit field. S7 is the register source 1, so the number 23 will appear in that field, and T0 is the register 5, is the destination register, and the number 5 will going to appear in that field. So the fields, the bit fields for this instruction format, for the R-type format, include the opcode. The opcode is used to specify the operation and the format of an instruction. And we're going to look at the number of bits for each one of those fields in a minute. Then we have the destination register operand. We have a function tree code that partially specifies a variant of the instruction to be executed. We have the first register source, and we have the second register source operand. And then we have the function 7 code. It's a function code that specifies the variant of the instruction to be executed. So there are two parts of the variant of the instruction that are specified, one in function 3, the other in function 7. So if you look into more detail, we see now the number of bits dedicated for each one of the fields. Notice first that each one of the registers has a field formed by 5 bits. The reason we are using 5 bits to specify each register is because there are 32 registers in RISC-V, so they'll be numbered from 0 to 31. We need 5 bits to specify numbers from 0 to 31. Remember that 2 to the 5 is 32. So, and this is the opcode for the add instructions, and the function code and function 3 and function 7 are variants to an arithmetic and logical unit instruction, In the case of the add instruction, this variant is the variant 0 in both codes. So we can convert this number now to a hexadecimal number by reading groups of 4 bits from the instruction sequentially. So in memory, this instruction will appear as that value 0x015B8 2B3. So if we connect back to the organization of the computer that we saw last time, you may recall that when you start executing an instruction, the processor will send the value of the program counter to the memory, obtain the address that's there, and immediately increment the program counter. That's why the program counter here appears as 800.100C. And the instruction that came from 800.10008. It was the last instruction that was fetched. And that word, we said last time that it went into the instruction register and was decoded by the processor. So now you know how the processor decodes that instruction is by looking at this format and decoding each one of those fields to find out that that was the add instruction. So after decoding, the processor will then have the information that this is the add of S7 and S5, putting the result into T0. So the execution of this instruction will now take the value from S7 and give as one input to the arithmetic logic unit, the value of 17 as the other input. There will be a code that will be taken from both the opcode and the variants in function 3 and function 7 that will tell the arithmetic logic unit that in this case, what it has to do is to add the two values that are in the input. It will produce an output, and the value from the output of the arithmetic and logic unit will then be sent to the destination register that in this case is 42. Another format for instruction is the format for a load word instruction. There is, for the load word instruction, a source register. The source register in this case appears on the left side. T0 is the register 5, S3 is the register 19. So the source register is, in this case, S3. This is where the address of the memory will be computed from. And the destination register in this case is the register T0, which is register number 5. So it's encoded in this fashion. The opcode for the load word instruction is 0x03. And the immediate value, that's the value that appears in front of the parentheses here, that's the displacement for the address, is specified in the top 12 bits of the instruction. So in memory, you'd see this value, and this is whenever the processor sees a word that came from memory as an instruction with this very specific code, it will know that it has to do a load word from S3 with a displacement of 23 and put the result into T0. A store word has a different format, it's an S-type format. And for the store word, the immediate value is split into two different areas in instruction. Otherwise, it's very similar to the load word. In this case, T0 is register 5, T1 is register 6. Note that the store word has two source registers and no destination register. No register is changed by store word, but the change happens in memory. So this is the encoding for that store word. Note that the immediate field is the encoding of the number 1200, and the bits 0 to 4 of the immediate field appears in the bits 7 to 11 of the instruction code, while the bits 5 to 11 appears in the bits 25 to 31 of the instruction code. So in memory, you'd see that hexadecimal value. Whenever we fetch that hexadecimal value, we're going to decode and find out that this is the store word instruction that we need to execute. So 1200 is actually this binary representation, and this animation shows how you take the binary value and you break into two pieces in order to encode the instruction. There are instructions that have an immediate operator. For example, the load upper immediate instruction has an immediate operator that has 20 bits. So the value for the immediate appears in this case in the bits 12 to 31 of the instruction. There is a destination register and an opcode. The binary representation will be in this format, and in memory you'd see that hexadecimal one. So thus far in this part of the lecture, we have learned that instruction formats are very specific, and by decoding, by breaking the 32 bits into different bit fields, we can find out, looking at the opcode, what type of instruction we need to execute, and looking at the other fields, we can find out which registers the instruction is operating with, and which displacements or immediate values it has. So what we have seen here is, for example, the instruction format is always a 32-bit word. It's divided into the bit fields, and we need 5 bits to specify each one of the registers in an instruction. And in memory, the instruction will appear as a 32-bit hexadecimal number. Next part of this lecture, we're going to look at instructions for making decisions.